Scientists said they achieved fusion net energy gain, and then everyone argued about whether that was even true. In December 2022, a lab in California announced that a fusion experiment produced more energy than the lasers put into the fuel. Headlines called it a historic milestone. But physicists immediately started arguing about what that actually meant. The argument comes down to one question: what counts as the input energy? That number changes everything. In a fusion reaction, you take two heavy forms of hydrogen called deuterium and tritium, and you force them together. When they fuse, they release a burst of energy. That part is real and not controversial. The California experiment used 192 giant lasers, all firing at a tiny pellet of fuel at the same time. The lasers delivered about 2.05 megajoules of energy to that pellet. The fusion reaction released about 3.15 megajoules. So the output was bigger than the input. That sounds like a win. And in a specific, narrow sense, it is. The fusion reaction itself produced more energy than the laser light that hit the fuel. Scientists call this target gain, but those lasers are not perfectly efficient. To generate 2.05 megajoules of laser light, the facility pulled roughly 300 megajoules from the electrical grid. So for every unit of energy that came out of the fusion reaction, about 100 units went in at the wall. This is the part the headlines usually skipped. The experiment crossed one finish line while still being very far from another. For fusion to work as a power source, you need the total energy out to exceed the total energy in, including all the energy used to run the lasers, the cooling systems, the magnets, everything. Nobody has done that yet. A different type of fusion machine called a tokamak uses powerful magnetic fields to hold superheated plasma in place instead of lasers. Europe's GET tokamak set its own records, but it also still uses far more energy than it produces overall. Physicists use a term called Q to describe the ratio of energy out to energy in. A Q of 1, of 1, means you broke even. The California laser experiment got a Q of about 1.5 measured at the target, but a Q of around 0.01 measured at the wall. Neither number is wrong. They are just measuring different things. The confusion happens when people do not say which Q they mean. The target gain result genuinely matters to researchers because it proves the physics works at that scale. That is useful information even if it is nowhere near a power plant. Getting to a Q greater than 1 at the wall level is the actual goal for practical fusion energy, and that remains an open research problem. Most estimates suggest it is still decades away, though the timeline is genuinely uncertain. So when you see a fusion headline, the most useful question to ask is simple: which energy are they comparing? If you want to understand what other science milestones actually mean underneath the headlines, there are more videos here that try to do exactly that.